Hi, my name is Karen, and I'm a graduate student at Cornell working with Professor Kenneth Swallow. And today I'm going to be presenting our work on how we use recently encountered information to segment events. Day-to-day experience is full of continuous streams of sensory information. For example, when we're walking in a busy street, there are lots of things going on. Cars passing by, maybe some buskers on the street, a sea of people, and the different buildings that you see. We therefore seem to be confronted with new information at every passing moment. But despite this bombardment of sensory input, our experience still makes sense, and our understanding of it do not consist of never-ending bits and pieces of information. Rather, they're organized in discrete event units. For example, when asked to describe how did you start your day, we tend to describe it as a list of activities, such as I got out of bed, I walked the dog, I took a shower, had some breakfast, and then I get to work. So our memory and description of our experience seems to consist of event units that are separable from each other. We therefore seem to divide continuous experience into discrete events, a process we call event segmentation. According to event segmentation theory, our online perception is partly guided by our knowledge. For example, watching Mr. Bean here trying to order food, based on past experiences, we have a schema of what ordering food entails. And as we watch Mr. Bean go through the motion of ordering food, this schema integrates with the current perceptual input to form a representation of what is happening now, or an event model. This event model can then help us make prediction of what should happen next. But what happens when Mr. Bean's food had arrived? Now something different is happening. And if we were to use the same ordering food event model, then the generated prediction will no longer be accurate. Event segmentation theory says that this is the time when we segment, when there is a mismatch with what we are perceiving and the prediction generated by the event model. Now, this theory suggests that event segmentation seems to be partly guided by our long-term knowledge. But what about knowledge about the recent past? When watching Mr. Bean receive his food, does knowledge about him ordering the food influence the way that we process and segment whatever happens next? So in this talk, I'll focus on answering this question. How is information from the recent past used for segmentation? When processing continuous flow of information, different brain areas seem to process events at different timescales. And if we look at how often do different brain regions track changes between stable states within a narrative, lower order sensory regions switches between stable states at shorter timescales, suggesting local signal for segmentation. Whereas higher order regions switches between stable states at longer time windows, suggesting a more global signal for segmentation. Behaviorally, we also know that people use both local and global signals for segmentation. People can segment events in different granularities. Fine segmentation usually coincides with lower level or more local changes, such as character changes or changes in how characters interact with objects. Whereas coarse segmentation usually coincides with more abstract, higher level or global changes, such as goal changes. Our knowledge of events is also hierarchically structured. We understand goals as comprising of sequences of smaller action units. So this suggests that at least on some level, we need some retention of knowledge about recent actions and their relations to each other to understand what's going on and potentially to be able to segment ongoing experience. So how is recently encountered information accumulated and used for segmentation? To answer this question, we asked participants to segment 10-minute long movies, pressing the spacebar whenever they feel that an event had ended and a new event had begun. Participants segmented 2 movies in total, and they segmented each movie twice, marking the smallest and largest event changes or fine and coarse segmentation. Next, we chop up this movie into clips that are 1 minute long each and present these clips to a second group of participants, but this time with a 3-second white noise interruption in between clips. This interruption disrupts the continuity in which information can be accumulated. So when a new clip starts, recent information would be temporally more distant than in the first uninterrupted condition. To a third set of participants, we presented the same set of clips, also with interruptions, But this time, the clips were presented out of order. So in this jumbled condition, at the start of a new clip, not only would recent information be more distant, they would also be narratively incoherent. So in this design, all participants receive the same stimuli, but the difference is in the kind of information that they have at every 1 minute interval. So if information used for segmentation needs to be accumulated in a temporally contiguous manner, disrupting the continuity of the movie should impact segmentation. And we should see differences between the uninterrupted, abbreviated as U, and the other two conditions, interrupted or I and jumbled or J. And if information needs to be accumulated such that they form episodically coherent understanding of the movie, we should see differences between the jumbled and the other two conditions. To look at the effect of disrupting movies on segmentation patterns over time, we can calculate a metric called the agreement index, or how similar are segmentation patterns between individuals. To do this, we first transform individual segmentation performance as time series, indicating the presence or absence of a button press at every second. Agreement is then calculated by comparing individual time series with a group average time series, scaled for number of button presses. If individuals within one group or condition segment the movies in similar ways, we can expect relatively high agreement values. Individual time series from one condition can also be compared with group time series from a different condition. For example, individual from the uninterrupted condition can be compared to those from the interrupted condition. So this analysis can be illustrated in a correlation matrix where each individual segmentation in each condition is compared with a group segmentation pattern in each condition too. So in our case, if we expect disruptions in movies to influence segmentation, we should see lower agreement values when individuals from one condition were compared with others from a different condition. So in other words, higher values should be expected along the diagonal line of the correlation matrix, where individuals are compared with others in the same experiment condition. However, we see no difference in agreement between the three groups, suggesting that segmentation patterns are similar across the three conditions. Another way to look at segmentation pattern across time is by performing a spectral density analysis on the group segmentation data. So here, group segmentation performance is characterized as button press density estimates across time, and we can then extract different frequency components from the group density. And here we see that the components of group segmentation pattern over time are highly overlapping the three conditions, again suggesting that movie disruptions have minimal impact on overall segmentation pattern. But when looking at the number of button presses participants make at every 5-second interval of the 1 minute clips, we see some influence of movie disruption in segmentation. So particularly, we see this brief increase in segmentation at the start of every 1 minute clip in the jumbled condition that quickly stabilizes after the first 5 seconds. And this is apparent for both coarse and fine segmentation. So this suggests that when recently accumulated information forms an incoherent narrative with what is happening now, we briefly increase segmentation, potentially as a means to gather more information. However, we seem to not need much information at all, and that a 5 seconds worth of information is enough to make sense of what is going on now. So overall, the results from this first experiment show that disrupting the continuity and coherence of movies at every minute interval did not influence overall segmentation pattern, and that the effects of these disruptions were limited to a narrow time window. So, would we see larger influence on segmentation patterns with more extreme disruptions? To answer this question, we again asked a different set of participants to segment the 10-minute long movies. However, this time the clips for the interrupted and jumbled conditions were much shorter. They're set at 5 seconds. Data collection for the second experiment is still ongoing, so I'm going to present results from the interrupted and jumbled conditions. Looking at segmentation agreement, for coarse segmentation, we see significantly lower agreement when comparing segmentation of jumbled individuals with those from the interrupted group. We also see significantly higher segmentation agreement between individuals in the jumbled condition for fine segmentation, suggesting that individuals in the jumbled condition are segmenting the movies differently. And looking at the spectral density analysis, we see this strong 0.2 Hertz component in segmentation pattern of jumbled participants and the absence of the other frequencies that are present in the other two conditions. This observation is more prominent for fine segmentation, and this shows that participants in the jumbled conditions are systematically segmenting at intervals that coincide with the onset of a new clip at every 5 seconds. And this systematicity becomes more prominent for fine segmentation. So this suggests that for participants in the jumbled condition, when information cannot be coherently accumulated for more than 5 seconds at a time, segmentation is driven by low-level visual transients, such as clip onset, and not based on content. So overall, by disrupting the movies at 1 minute interval in experiment 1, we see that segmentation is pretty resistant to disruptions in information flow. And when disruptions affect coherence of the narrative, segmentation immediately following the disruption is impacted, but it also quickly recovers. But when movies are extremely disrupted at every 5-second intervals in experiment 2, we see more severe influence on segmentation. Interrupting the movie increases segmentation based on clip onset, and jumbling the movies diminish segmentation based on movie content. Now, what about the memory for the movies? Event segmentation is known to influence how we encode and organize events into memory. And we have seen that segmentation behavior can be pretty robust. When movies are disrupted at every 1 minute, segmentation remains unaffected. So would event memory be similarly resistant to movie disruptions, or does disrupting movies influence event memory? To answer this question, we asked participants to recall everything they remember happening in the movie following the segmentation task. Here, I'm just going to focus on recall from the first experiment when videos were interrupted and jumbled at every 1 minute interval. Based on our preliminary analysis, it seems that even though segmentation is intact, disrupting the movies at 1 minute interval seems to influence event memory. Participants in the interrupted and jumbled conditions recalled events using fewer words compared to participants in the uninterrupted condition. And participants in the jumbled condition also recalled events using fewer clauses compared to participants in the uninterrupted condition. Interruptions of movie coherence also seem to influence overall number of events recalled. And here, to quantify events recalled, we use Hauser et al.'s technique of topic modeling. So first, we manually annotate each movie describing every small detail such as action, location, or actor interaction changes. From this annotation, we have a bag of words that we can extract latent themes from based on word compositions. An event can then be described as a set of latent themes with different weight combinations, whereby each theme consists of a bag of words with various weights. These theme combinations can then be applied to participants' written recall script to identify the events that they remembered. And overall, participants in the jumbled condition recalled less events, particularly compared to participants in the interrupted condition, again suggesting that disruption in the ability to accumulate coherent information may significantly impair memory. So in conclusion, the study showed that behavior segmentation is robust and resistant to disruptions of the information stream, and that content-based segmentation can rely on local signals when information flow is disrupted. However, when it comes to event memory, it is a different matter. Event memory formation requires accumulation of continuous and coherent information over extended time. So we know from past studies that event segmentation is highly related to episodic memory formation. However, this study suggests that even though event segmentation and episodic memory may share overlapping mechanisms, there may also be differences. Particularly, their reliance on information from the recent past seems to be different. While event segmentation can rely on information at shorter timescales, episodic memory requires information at longer timescales. With that, I would like to thank my lab, especially the undergraduate RAs that have helped me with this project, the Psychonomics Organizing Committee, and thank you all for your attention.